Alright, so we're going to take notes here for section 2 in chapter 1, using segments and congruence. So we found out what a segment was last time. The collection of two endpoints and all the points in between them. We're now going to use that to extend our knowledge to do some things with those segments. You're going to hear a couple of funny words. The word postulate in this book is a rule that is accepted as true without a proof. Whereas a theorem is a rule in math that can be proved to be true. So postulates and theorems are things we're going to work with all year long. We're going to get the first of our postulates today. Proofs are only logical arguments that show a statement is true. We're going to do a lot of these in 2 columns. We're going to practice these a ton in a bunch of different ways. They're really what a lot of this class is about, working on your logical argument skills. Alright, so the ruler postulate. Remember, this is a rule that is accepted as true without proof. The ruler postulate says points on a line can be matched 1-to-1 with real numbers. The number that corresponds to a point is the coordinate of the point. So we're going to actually skip down to example 1 to see how this works real quick. The ruler postulate says if you have 2 points, so here's our 2 points, and you make a line in between them. So we're taking the line segment. If you measure, take a ruler, doesn't matter what the units are, line 1 unit up with the first point, and wherever the units on that last point wind up, subtract the 2. So C wound up at unit 1, D wound up at unit 4.7. So if you subtract them and then take the absolute value, 1 minus 4.7 is negative 3.7, but we have to take the absolute value of that. The absolute value of a negative number is a positive number. So 3.7 is our number, and then we slap the units back on there, centimeters. That's all the ruler postulate says. It's really a way for them to try to tell you to measure something. It doesn't matter whether you start at 0 and measure the length, or whether you start at any point and then measure the length and do the subtraction and take the absolute value. You'll get the same number. The ruler postulate. We're going to scroll back up. Now we get into some serious, important geometry stuff. The length of a segment. The distance between the 2 endpoints. Length is written as the capital letters of the endpoints without any lines or arrows above it. So when we're talking about length, the number of units associated with a segment, it's just the 2 endpoints with no line above them. AB, those 2 letters together are telling you that you're dealing with the length, the distance between those 2 endpoints, A and B. Distance, as we just saw, is the absolute value of the difference of the coordinates of the points, straight from the ruler postulate. And the distance between 2 points is the length of the segment that has those 2 endpoints. Length, very important that we know that it's also distance. We do have a distance formula. The distance formula in the coordinate plane can be used to find the length of a lot of segments in the coordinate plane. Distance in the coordinate plane, something that you should have memorized. If you don't, memorize it now. Stat. ASAP. Alright, this is the important part. You got to know the difference here between a segment, the physical object, and that segment's length. One has a line on top, one does not. We'll be using these to go from numbers, where we can use everything we know about equality and the properties of equality, to manipulate our numbers back and forth to the physical objects, the segments. Eventually we'll build up enough so that we don't very often have to use the lengths, where we'll just be able to stay in the physical world with the physical objects. But we have to build up to that point. How we do that is we go from the physical objects to the lengths so that we can say things and prove things using the properties of equality. And then we prove things about the physical objects. And as we prove more things about the physical objects, we can use those things that we've proven to do more things instead of falling back to the properties of equality. One of the ways we do this is with the segment addition postulate. Second postulate of the day, far more important than the first postulate of the day. The ruler postulate tells you to measure something. The segment addition postulate is something that you have to be able to look at and know that you can use. If a point is between two other points on a line, then the length of the whole segment is the sum of the two shorter segments. Two segments can add together to make a longer segment in a line. That between word, very important here because it's the point that tells you that this is a straight thing. C here has to be in between A and B. We know how to write length as two letters thanks to our last definition, the length of a segment. So this says the length of the whole segment is the sum of the two shorter segments. So the two shorter segments are AC and BC. Sum means add those two together, and it should equal the length of the whole segment, which is from A to B. The letters here aren't important because we're going to do this with lots of different segments. It's the fact that one point is between the other two, then you can add up in a line those segments. The first segment plus the second segment has to equal the whole thing. So we're going to use this a lot, especially here at the beginning of the semester. The segment addition postulate is one of our fallback elements that we use throughout the year whenever we're stuck on things. It's a go-to entity. It's very powerful in reality. It lets us do a lot of stuff. And our last definition, big definition here, congruent segments. If the length of two segments are equal, then the segments are congruent. Here's our symbol for congruent. It's an equal sign with a wavy line on top. So this also works the other way. If two segments are congruent, then they have the same length. We're going to be writing things like this a lot over the semester. So learning these shorthand abbreviations, if two segments are congruent, then they have the same length, saves you a lot of writing. Definitions have two if-thens associated with them, which are flip-flops of each other around the then. We'll get into why that is in Chapter 2. Congruent, we talked about being an isomorphic mapping of one onto the other. So if it's congruent, yes, there is an isomorphic mapping of one onto the other. There's a way to translate, either shift left, right, up, or down, flip, and rotate so that the two images match each other perfectly. Looking at these two, can we say what that is? What do we do to all the xy points of AB to take them to DE? I don't know. Because there's no axis here, there's no coordinate system set up, even though we know they're congruent, we can't say what that mapping is. We know that there is one because we know that they're congruent. The isomorphic mapping, we know, keeps the lengths and the angle measures the same. Well, in segments, are there any angle measures? There are no angles because it's just a segment. And so the only thing we have to worry about is it keeping the same measure. And that's the very definition of congruent segments. A congruent segments are two segments that have equal length. And so by their definition, they're automatically isomorphically mapped. Marking diagrams is a big thing in geometry. We mark these diagrams with tick marks to show that they're congruent. And let's go down to our examples. If you need to take a little break, get a drink of water. This is a good place to pause, collect your thoughts, and then come back. Example 2, find the length of KL. So we're trying to find the length between the points K and L. The good part is we should all be able to look at this and say, oh, if we already have 15 and we want to get to 38, then KL should be 23. Geometry, though, says we have to use postulates, properties, definitions, and theorems to do our work. And so what we were really doing there is using the segment addition postulate. We know that JK plus KL equals JL. Segment addition postulate. SAP. We can now substitute in the numbers that we had. JK, we know, is 15. It's given in our diagram. KL is what we're looking for. And JL is 38, also given in the diagram. And now we can solve the equation to find KL. So with that equation we have, what would we do to solve it? We would subtract 15 from both sides of the equal sign. So that KL is 23. We don't have any units in our diagram, so we don't have to put any units on KL. The steps, we substituted here, replacing something with what we know it's equal to, and then we use the subtraction property of equality and simplified to get our answer. So that's one of the big differences here between geometry and, say, pre-algebra and algebra. This is a pre-algebra problem if they just want you to say what KL is. Well, what's KL? You could give that to a lot of 6th and 7th graders and they can tell you that KL is 23. So that's obviously not the entirety of what we're looking for. We're looking for this advanced thought process. How did you set that up? How did you get to KL being 23? Can you explain to me what postulates, properties, theorems, and definitions you used? The more often you can think like this, the easier geometry will get for you. We will see an example 4, which is using this with a much harder algebra problem where the setup is a little more helpful for most people. Most people don't like to have to show their work like this because 38 minus 15 is 23, sweet. But if you don't show your work like this, then the only problems I can give you are the really hard problems to force you to show your work. So you want to show your work on the easy problems so that you don't have worksheets of entirely hard problems. So we're going to go down to example 3. Plot the points F, G, H, and J. F, G is the point 4, 5. F. G is the point -1, 5. -1, 5. G. H is the point 3, 3. H. And J is the point 3, -2. Points plotted, easy. R, F, G, the segment, and H, J, the segment. Congruent segments. Explain. All right, so we could use the distance formula because we have coordinate points in the coordinate plane, but these are vertical points and horizontal points, which means we can just use the ruler postulate to measure the horizontal distance and the vertical distance. we go from -1 in the x direction to 4 in the x direction. So -1 minus 4, the absolute value of that is positive 5. This is the ruler postulate that we just used. And then we simplified, and then we simplified. Now let's do the same thing in the y direction. In the y direction, we go from h, which starts at 3, to j, which is down at -2. So we have the ruler postulate, 3 minus -2, which is 3 plus 2. The absolute value of positive 5 is still 5. So ruler postulate, usually we can abbreviate postulate to post. And we simplified, and we simplified, and we simplified. What two things did we just find? We found the length of GF. So GF, its length, the segment length, is 5. And we found HJ. The segment length there is 5. If two segments have the same length, then you might have to go back and look in the notes, but they are congruent. So the segment GF is congruent to the segment HJ because GF is equal to HJ by substitution. So, what are we substituting? We're recognizing that the 5's are the same, and then changing one of the 5's into what we know the other 5 is equal to. So if we change this 5 into what we know this 5 is equal to, that's where we get GF equals HJ. That's substitution. It's a little strange to see variables like HJ replacing the numbers, but it's still substitution. It's still doing that same concept from Algebra 1, replacing something with what you know it's equal to. And let's go down to do our last example, example 4. Solve for x in the length of GR given that GR is 2x squared. Oh, well, those aren't right. So apparently I fixed that, I think, on the worksheets you guys should have, but not apparently on mine. Interesting. So hopefully you have RZ equals 9x and GZ equals 18. If not, just change it. We're going to use the segment addition postulate. We look at the picture over here. Oh, look at the picture. R is in between GZ. So the sum of the two smaller pieces, GR plus RZ, equals the whole length, GZ. And now we can substitute, replacing GR with what we know GR is equal to, 2x squared, plus substituting, replacing RZ with what we know it's equal to. And lastly, substituting, replacing GZ with what we know it's equal to. Now we have an algebra problem to solve. So we recognize that it has a squared and a linear term. So we should probably try to factor. To factor, we want to set one side equal to 0. So we're going to start by subtracting 18 from both sides, using the subtraction property of equality. The more we think in terms of what property are we using, what postulate, theorem, definition are we using, the easier geometry gets. So I don't just subtract 18 from both sides. I subtract 18 from both sides and think I'm using the subtraction property of equality. I'm going to do some scratch work off to the side to figure out what I need to do next. I'm going to multiply the first and last terms together to get negative 36. I'm looking for what multiplies together to be negative 36 and adds together to be 9. So negative 1 times 36, negative 2 times 18, negative 3 times 12, add together to be positive 9 for the middle term. So I found what multiplies together to be negative 36, adds together to be the middle term. I can split my middle term up. Negative 3x plus 12x is the plus 9x on the line above it, so that I can factor out the common factor of my first two terms. I can factor out the common factor of my last two terms. Both of those factorings are using the distributive property backwards. This is how factoring works. So now we have the 2x minus 3's in common, and we're going to factor out that common factor using the distributive property backwards again. And we have factored. We factor so that we can use the zero product property. If two things multiply together to equal 0, either one of them equals 0 or the other one does. We have two equations to solve. So using the addition property of equality and the division property of equality, and using the subtraction property of equality on the other side, we get two answers for x. If we plug in the negative 6 to RZ, we would have a length of negative 54. Lengths cannot be negative, so we know that this is an extraneous answer. It doesn't make sense for our problem. Since our length has to be positive, we have one more chance, 3/2. When we plug it into GR, we don't have any issue. When we plug it into RZ, again it's positive, so we don't have any issue. We want to find the length of GR, because that's what it's asked for up here. So GR is 2x squared. We are going to substitute, changing the x into what we know the x equals, 3/2. We're going to square 3/2. So we square the top and square the bottom, 9/4. We're going to multiply the 9/4 by 2, which is 2 over 1. And so we get 9/2. There's a couple of ways to do that. 2 over 1 times 9 over 4, you can cancel. 4 is 2 times 2. So one of the 2's can become a 1. 2 divided by 2 is 1, leaving you with 9/2. Or you could actually do the multiplication. 2 over 1 times 9 over 4 is 18 over 4, and then divide both top and bottom by 2 to get the 9/2. So any way we go, we get GR is 9/2. There's our answer to solve for x, and here's our answer for the length of GR. Very important stuff going on today. Segment length, congruent segments, and the segment addition postulate. Try the checkpoints, check to see if your answers are right. mark down any questions that you have so you can ask tomorrow, and I will see you all then.